Great White North. Dr. Prochazka is at the University of Alberta. He was trained at the University of Ulm in Germany, and he and his colleagues helped elucidate the nature of sensory input during voluntary movement. His recent work includes modeling spinal cord activity and the neuromechanics of locomotion. Particularly interesting is he's been using neuroprostheses to improve hand function after stroke and spinal injury. And these involve the use of implanted neuroprostheses called StimRooter and a computerized exercise workstation called Rejoice, which is for rehabilitation joystick for computer exercise. This involves internet-mediated telesupervision, and it's already moved into the United States. It's moved across the borders. So it's just what we've been talking about that we need. It's not enough to do these kinds of intensive practice, et cetera, for a short period of time, a relatively short period of time, 3 times a week or even 5 days a week. We need to have an all-enveloping environment to keep people practicing in an engaging, interesting, challenging way. So we're very delighted to have Dr. Prochazka. Am I pronouncing your name properly? Close enough. Okay, and I now turn over the floor to you.
So to take a leaf from, 3 seconds. There we go. I'm going to take a leaf out of Dr. Goffer's book and sit here because I can then control the videos and so forth. I'd just like to thank Carolee Winstein and Mindy Eisen for including me in this program. I wasn't going to be part of this till about, 2 days ago? But it just so happens that I've become a kind of honorary, what do you call, Angelia? What's that? Angelia, because my wife and I recently got a small place in Long Beach. So I'll be around polluting this neighborhood a fair bit, I hope. So as Carolee very kindly introduced a lot of what I'm going to talk about, I'll be just filling in some of the details. So the problem, of course, that people with stroke have is illustrated by this video. This is one of our subjects doing a part of the so-called ARAT, hand function test. Notice he has a lot of trouble not only in placing the object but also in releasing. He can't open his hand. And in tetraplegia it's a little bit different. A lot of trouble picking up objects. In this case, mainly problem with grasp, not enough force in the movement. In fact, in a very well-known, I'd say almost famous study just a few years ago by Kimberly Anderson, who herself is in a wheelchair, tetraplegic, she interviewed people with tetraplegia and paraplegia and came up with the following wish list, and you'll see that that for tetraplegic people, arm and hand function is way, by far, at the top of the list of things that they like improvements in, arm and hand function. Ahead of sex function, trunk stability, bladder bowel, and so forth. So it's a really important problem, also for strokes. So currently, the way this is tackled in rehab hospitals all over the world is with very simple exercise protocols using objects such as the ones shown here. And I always think, someone goes through their life, maybe rearing kids and running businesses and so forth. You start by playing with things like building blocks and so forth. And in the end, you have to do this again. And I think, to me, it's somehow demeaning. So, forced use exercise, or as it's now known, constraint-induced movement therapy, has been shown to be beneficial for people with stroke. And this is a conclusion from the evidence-based review of stroke rehab, which is a very important resource on the internet out of UBC, University of British Columbia. And if you haven't referred to this, then I'd strongly recommend it. There have been hundreds of thousands of hits on that website. So constraint-induced movement therapy consists of, well, in its current form anyway, 6 hours a day of repetitive exercises. This is clinic-based, although there have been some attempts, I think, to transfer that to home use. Modified constraint-induced therapy, introduced by Stephen Page, is 1 hour a day for 6 weeks. And this is also done in clinics, again, involving fairly repetitive tasks, but at least in many cases approaching those of activities of daily life. The real thing is, how do we maintain interest amongst people, particularly once they go home? They're not going to want to sit around playing with building blocks, and in fact they just refuse to do it after a while. The next part of our approach is to use functional electrical stimulation, and as many of you probably know, Rancho Los Amigos Hospital was the center of FES with McNeil, Bowman, and other people in the 70s. And so it's in a way a privilege for me to be sitting here giving this talk. It's the first time I've been to the Rancho. And so again, the evidence-based website for stroke says there's strong evidence that FES improves upper extremity function in acute stroke. They also came to the following additional conclusions: that FES and exercise was effective in 13 out of 22 stroke studies, and it was best when the electrical stim of the hand was triggered by the person themselves. And this comes back to something Cara Lee said, and also Dr. Goffman. So as far as spinal cord injury is concerned, there's a similar website, and the conclusions there are that FES, functional electrical stimulation, improves function. But the problem is that FES, by and large, is only available in rehab centers, and the costs still remain very high for devices. So we now know with reasonable certainty that if we combine FES with exercise training, we're going to get good improvements. But how can this be delivered cost effectively and at home after people leave the rehab environment? Surface FES stimulators have been around for quite a while, starting with physiotherapy stimulators in the 70s, and then moving on through EMG-triggered devices such as the NeuroMove. Currently, the Bioness H200 is on the market and probably used in this hospital. And at about the same time that was developed in Edmonton, we came up with this device which was intended for spinal cord injured people, and that was triggered by wrist movements. Here's a quick movie of someone using the Bioness H200, but notice, again, it's the building block approach. Not sure why the sound isn't coming through. Well, maybe it doesn't matter. Oh, I'm not going to struggle. It really doesn't matter. Oh, that's a good point. That's a good point. There we go. That's cool. Thank you. Now, the Binance H200 costs around about $6,000, and that puts it at the sort of top end of what can be afforded by stroke patients, for example. There have been studies showing that it's effective in assisting in tasks like these, picking up a phone, using a fork, and so forth. But it's not really intended as a device to be used at home. It's really clinic-based. So our approach has been to come up with devices that could be used at home that are cheaper. So the one we're working on and will be available later this year will cost about $3,000. So here's a video of a person with tetraplegia, C5, C6. He's wearing a little earpiece, a bit like a hearing aid, and with a sensor that goes just behind a little cartilage called the tragus at the front of the ear. And that sensor picks up vibrations that are set up in the skull by very small tooth clicks. He will be opening and closing his hand with tooth clicks, so the device sends a radio signal down to the stimulator, which is down here, and the stimulator has electrodes that open the hand and also flex the fingers and adduct the thumb. So you have to watch very carefully to see the very tiny tooth clicks that he is producing in order to trigger the device to open and close his hand. So if you watch very carefully, you might just see a tooth click there, very small. So it's a nice discrete way of controlling stimulation. Of course, there is quite a history of implantables for doing this sort of thing. The Neuro-Control freehand system, Hunter Peckham's device, and then also more recently Jerry Loeb's Bion, which was tested in a number of people for shoulder subluxation. And this is a device that can be implanted next to a nerve through a catheter, and then a radio transmitter provides power through the skin to the Bion, picked up by this coil here. It was actually developed initially in Canada when Jerry was at Queen's University. And so the idea is to implant these Bions next to nerves. I'm not quite sure, I mean, it's a brilliant idea, and I'm not quite sure why it hasn't taken off. And there are sort of business commercial reasons for that I don't understand. But you would think that that would have been a very successful device. We came up a few years ago with an alternative approach, which is to implant a lead that went from a conductive end under the skin, insulated down to a nerve cuff, and then the idea being that if you pass current through the skin, trains of current pulses, that would then, some of the current would flow down the lead and stimulate the nerve. We have actually managed to get patents on this and got a lot of resistance from the US patent examiner, and quite recently for a continuation in part patent. And his comment was, I've been trying to knock this patent down. I've put more time into this one than any other patent, because what you're trying to do is patent a wire. And that's exactly what it is. It's just a wire that goes from one point under the skin down to a nerve. And then that picks up current that you deliver through the skin with surface electrodes. So the idea being it's a cheap way of doing a neural implant or a neural prosthesis, because you're just implanting a wire and then everything else, all the smarts, happen on the outside. Jan Kowalczewski, a grad student of mine at the time, came up with a very nice nerve cuff which is a bit like a tie wrap, really, and that has been implanted now in 3 people in Edmonton. Here is an example of where the stimulator is not on. So this is a guy who's been implanted. He's controlling the stimulation with 2 clicks. The current is flowing through his skin to the implanted stim router lead. And here is his performance when the current is turned on. And so now he's clicked it and got a sufficient grasp to be able to open that rather sticky pill jar. And I'll just play this one quickly. This hand open, hand close, nice strong pinch grip, strong enough to open the lunchbox, which he couldn't do without the stim on. One of the important things is that when people take these devices home, often in the past, eventually the device has been discarded. People, for whatever reason, don't use them after a while. So it's important to know how many hours per day or per week the device actually being used. So we actually have an automatic counter in our stimulator that counts the number of hours of usage per week. And in this case, don't have to go into the details, but it's very useful because there are some occasionally down periods like this one here, and that was correlated with him having an unrelated health problem. So our choices for functional electrical stimulation currently are the Binez H200. Later this year, we're coming up with our own FES wristlet, which will cost about half of that, and it'll be controlled with head nods, very similar to the tooth-click approach. And in the future, perhaps stim router implants. So how do we make the exercises more interesting, keep compliance up, and also allow people to do exercises in a meaningful way? So what I did, and I'll just go through this very quickly, I looked at robotic approaches, and we'll be hearing more about those a bit later on this morning, and particularly looking at the cost, because it's one thing to provide something like this in the clinic. It's another entirely to expect it then to be used in people's homes after they leave the clinic. Also, the cost issue, typically actuated robots cost between $50,000 and $100,000. Most of the ones that I surveyed did not really provide practice of dexterous manipulation. In other words, hand prehension, grasp, release, twisting, pronation, supination, and actually doing things with real-life objects that have weight and resistance. Also, the question of maintaining compliance by contacting the person and speaking to them on a daily basis we've found to be very important. And so far, I don't think, with the exception of, I think David Reinkensmeyer might have done something like this. I think we're probably the first to have done consistent tele-supervision of in-home exercises. And it's not always the best thing to be the first to do something, because it's expensive, you make a lot of mistakes, and then someone else comes up behind you and does it faster, quicker, better, for less money. So I hope that's not going to happen to us. Then there are small rehab robots that cost a lot less. I don't know how much the InMotion device costs, but maybe we'll hear about that later on. Stephen Wolf's hand, well, actually I was told by Stephen that it wasn't his device, right, but he has something to do with it. Right. Yes. He's a consultant for this device here. It doesn't allow full range of motion. It's basically in one position, but at least the cost is down, and there are computer games. It does have weight support. So far as I know, no tele-supervision. So the conclusions for robotics are that, yes, they, and I think Carol Lee touched on this, that they appear to produce recovery that's similar to that can be produced with therapy, one-on-one therapy. But an interesting paper was published a few years ago that asked the question, does it really matter what the robot does? And the conclusion really was, no, it's what the person does. And I think that's important, and that produces improvements. And I think this also is something that we've heard in both talks this morning, that the person has to be in control and be motivated. There are passive exercise devices. I won't go into the details of these. They're quite expensive and not suitable for home use. The Armeo Boom is probably the closest, and that's a new device by Hokoma, the same company that produces the Lokomat. Around $19,000, has full range of motion. It's basically a sling support, and then computer games can be played by moving the arm around, but no dexterous manipulation as far as I know. The Nintendo Wii is very low cost, of course, used in rehab clinics all over the world now, and great for range of motion exercises, but no dexterous manipulation, weight support, or tele-supervision, so far at least. So that brings me to our device, which has already been talked about, and so I don't need to go into it too much, except to say that on the end of this spring-loaded arm, there are a number of objects here that the person has to manipulate in different ways. So there's a peg at the top that they have to grasp and pull up with an index thumb apposition. There's this yellow part here is like a jar top that has to be swiveled or rotated. Then there's a doorknob, then there's a key, and then there's this thing, we call it the gripper, and so force has to be applied to the gripper. And all of this then is integrated into a tele-rehab system with computer games. And in this video clip from the University of Melbourne, which is doing a study of this device in subacute spinal cord injured people, I think this kind of summarizes the way it works quite nicely, in addition to that video that Carol Lee showed.
Computer games are helping 28-year-old Gabriel Moretas, who suffered a spinal cord injury after a motorcycle accident, to try and regain movement of his hands. The workstation, called the Rejoice, allows spinal cord injury patients in a new University of Melbourne and Austin Health study to undergo home-based rehabilitation. It is being used for the first time in Australia in tele-rehabilitation, which allows patients to get real-time specialist physiotherapy over the internet.
It can be installed in their own home very simply, and people can use it in the comfort of their own home without having to travel, and the tele-rehabilitation enables the therapist to still keep in touch with them to monitor their progress. That, I think, is a very important way of continuing to enable people to keep on improving.
The patient wears a glove that enables electrical impulses to stimulate the muscles in the hand to grasp and release. It is hoped that this will sprout new connections in the spinal cord and re-establish hand function.
So just moving on here, the Rejoice also has an automated hand function test. I'll just play this video, which is part of the test. Every part of the hand function test it involves the computer telling the person what they have to do. The person then attempts to do it as best they can, and the amplitude of movement or the time taken are measured, and then we come up with an overall hand function score.
You'll notice that the handle is flashing. Grasp it and lift it as high as you can, just like this.
So in response to that, the subject would do this. And then there are other parts to the hand function test, like lifting a peg, twisting the doorknob, twisting the jar lid, and so forth. It takes about 4 minutes, tests range of motion and dexterity, generates a log automatically, and it can be used to calibrate the difficulty of the games that the person plays. So we have this thing called a suggestatron. It suggests the difficulty level, and it also suggests the type of game the person would be able to do. Because if they can't lift the peg, then they can't play certain games. My favourite game on this is the bartender game. It's a little bit like the one Carolee showed. And so you start with this very derelict-looking bar with rather down-market customers coming up and demanding drinks. And then you have to select, you have to sort of go up here, pick the drink that they want and pour. And just like in your case, if you miss, then you don't get any points for that. And if you do well, then you get a better bar, and the class of customers improves. So we have done some correlations between the automated hand function test and the ARAT, that's the Action Research Arm test, and Fugel-Meyer, and they correlate reasonably well. So just quickly, we've done a few studies now, I've published a couple of them. The International Spinal Research Trust pilot study with 13 subjects, 18 hands, some of them did it with both hands. And it was a crossover study where the ARAT was tested at fortnightly intervals, and then so in this group here, the top line shows patients who started with the rejoice, and then they crossed over and did 6 weeks of tele-rehab with just standard exercises. And so the rejoice first group did quite well. They exceeded the minimal clinically important difference within 2 to 3 weeks. And the rejoice automated hand function test pretty much mirrored those findings. The hand function test allows us to look at particular improvements in particular tasks. So, for example, this green line here is the key and the key rotation, and that did not improve over these few weeks. Whereas some of the other tasks, like placement and so forth, improved a lot. And then from all of these individual tasks, we get the mean. These are some of the reported improvements in activities of daily life. Remember, these people are using the device at home and also using the stimulator at home as well. I won't go through the list, it's fairly long. More recently, we've done a 3-center, it's another pilot study, convenience sample really, of people, and seen similar improvements in hand function. Interesting that the people in Toronto did less well, so they improved by 10% or so, but not as well as the people at UBC in Vancouver, and we wonder why. And it's all to do with where they started. So patients starting at a lower level of functionality didn't improve as much as patients starting at a higher level. And when we looked at this more carefully, it was clear that if they started somewhere in the middle of the ARAT, they improved much more, so in this case about 13%, than people who were higher functioning or lower functioning. So that's an important thing to know. We've done studies in stroke patients, I won't go into the details, but similar types of improvements over time. Currently we're doing a study partly based in Belfast, partly in the UK, and partly in
So if you position your right hand on the gripper. Yeah, perfect. Okay. And whenever you're happy enough, we'll start.
One additional thing we've done here is we've used transcranial magnetic stimulation as well as our other tests. And One novel feature of our TMS approach is to use accelerometers instead of, well, in addition to EMG. So motor evoked potentials, but also twitches of the finger and wrist recorded with accelerometers. And that's actually a much quicker and easier thing to do. And the two things are pretty well correlated. So acceleration and MEPs are pretty well correlated. Preliminary results similar to what I've already shown. I won't go into the details. So summary of the studies so far. It's the first multi-center trial of in-home tele-rehab. The automated hand function test allows quantitative comparisons between centers. Not always possible if you have different raters in different places. There was a large range of improvement from people who didn't improve at all to people who improved by 35%. That's a lot on the arrow or the raft. And those were the medium functioning ones who at baseline. Improvements lasted about 6 months and began declining after that. We actually, interestingly, didn't find a very good correlation between the TMS responses and our clinical hand function tests. I don't know why. And the efficacy of FES, in addition to the exercise, is unclear at this point. We still need to do more studies of this. And then the stimulator implants I mentioned. So these are the places that the rejoice has spread to so far, and not always, like for example in Florida, I'm not sure that they've done much with that. So it's quite variable. The cost is very important. The rejoice workstation and so forth, all the different bits to it cost around about $10,000. The hand stimulator will cost about $3,000, and that's out of the reach of most people. And in addition, you don't need to keep the rejoice workstation at home. So the idea is to rent the rejoice out and provide tele-supervision sessions. And an example is 8 weeks rental of the devices plus 16 tele-supervision sessions would cost about $3,000. What we need to do, and I'm hoping some of this can be done here in Los Angeles, would be very nice, is to do a feasibility study of tele-rehab in the United States. Because in Canada and other jurisdictions, we have different health systems, as I'm sure you know. And what we need to know is, because the US is really the main market in this part of the world, we really need to know whether this is going to be accepted into the system and whether it can cross state boundaries, for example, and whether it's going to get reimbursed. But we also need to do more randomized controlled trials of different combinations of exercise and FES. We need to find out whether FES wristlets used in activities of daily life, how much they're used by stroke patients, for example, improvement in function, and also, very important, satisfaction. And Dr. Golfer talked a little bit about dignity and so forth that's related to that. And we need to do cost-benefit analysis and develop a strategy to go to CMS for reimbursement. Just one last little quick thing in relation to a talk that Dr. Anderson's going to give later on. We've also spent a bit of time developing devices for computer control, but not a brain-computer interface, but just a gyro tooth-click head computer interface. I don't know, we have to develop an acronym for that. But what this is, so he's wearing one of these earpieces. In it, there's a gyro, 3-axis gyro, which detects head movements, and also a tooth-click sensor. And so you'll be able to see what he can do very quickly just using this device, the cost of which would probably be, if once it was commercialized, would be under $2,000. He's basically just surfing the net here. He's clicking, he's double clicking, he's click dragging, he's moving the cursor around quickly. And so that's using a pretty simple approach. And so the question really is, we should be, I think, when we're comparing brain-controlled interfaces, we should also be comparing their performance to something that's pretty simple and relatively cheap. And we should be doing it with the ISO standard that is now currently the standard way of comparing mouse pointing devices. And so that's out there, and it's to do with, there's this thing they call the index of performance, and that's what I think we should be measuring. I'd just like to acknowledge all of the people who've helped us get to where we are and our funding agencies. And thanks very much again for inviting me. Do you want to switch over the